Every year, more than 4 million tons of pesticides are sprayed across farmland worldwide. Rice paddies alone, the primary food source for over half of humanity, absorb around 10 to 15% of that chemical load. Over time, soils become exhausted, microbial life disappears, and pests adapt faster than ever before. And it is precisely in this context that a seemingly unbelievable scene emerged in southern China. Thousands of ducks released freely into active rice fields. No fences, no chemical pesticides, no conventional control methods. To many, it looked like madness. But after just one growing season, something remarkable happened. The rice survived. Yields did not fall. Costs dropped. And the ecosystem began to return. How can a flock of ducks replace chemical pesticides? And how does an ancient farming practice challenge the very foundation of modern agriculture? Taran Works reveals it all in this video. For most of human history, growing rice meant manual labor, unpredictable weather, and high risk. But as the 20th century began, everything changed at a pace that was hard to imagine. Rice transplanters replaced dozens of hands in the fields. Combined harvesters shortened harvest seasons from days to just hours. Nitrogen fertilizers accelerated plant growth and made yields more uniform. Pesticides allowed farmers to control pests across vast areas with a single spray. Rice cultivation entered an era of standardization and scale. In the short term, the system functioned almost perfectly. Output surged and harvests became more stable. Yet that very efficiency concealed silent fractures. Repeated pesticide use pushed pests to evolve resistance faster. Excess fertilizers washed into rivers and lakes, triggering eutrophication and polluting water sources. Soils gradually lost beneficial microorganisms and became increasingly dependent on chemical inputs. Slowly, a paradox emerged. Production increased, but profits declined. The costs of fertilizers and pesticides kept rising while the land responded less and less to the very chemicals that once drove its productivity. And as these limits grew impossible to ignore, a question surfaced. Is there any path forward other than pouring ever more chemicals into rice fields? The return of the rice duck system in the 21st century. The answer did not come from high-tech laboratories, but from agricultural history itself. In the early 2000s, groups of scientists in China, Japan, and Southeast Asia began to re-examine farming systems that had long been neglected. Among them, the rice duck system emerged as a particularly striking case. Rather than dismissing it as outdated folk practice, researchers brought this model into controlled experiments and measured its effects with concrete data. The results surprised many. Rice fields integrated with ducks recorded a 50 to 70% reduction in pesticide use along with clear declines in herbicides and chemical fertilizers. Some studies even showed yield increases ranging from 7% to more than 15%, especially in fields suffering from soil degradation. In China, provinces such as Shuang, Fujian, and Guangdong saw farmers gradually reintroduce ducks into their rice paddies. At first, these were only small exploratory trials. But as the results repeated themselves across multiple growing seasons, the model quickly scaled up from a handful of plots to entire farming regions. So why ducks and not some other animal? In the rice duck system, ducks are not auxiliary livestock kept outside the production process. They are an integral part of cultivation. True ecological engineers. Few animals are as naturally suited to rice paddies as ducks. They thrive in shallow water, move constantly yet lightly, and when introduced at the right stage, they cause almost no damage to the rice plants themselves. Instead of feeding on rice, ducks focus on exactly what farmers want to remove. They consume harmful insects such as brown plant hoppers and stem borers along with various aquatic organisms that compete with rice for nutrients. At the same time, ducks pick at young weeds, disrupting their life cycle before they have a chance to establish and spread. The most significant impact, however, comes from movements that seem almost ordinary. As ducks walk through the fields, they stir the water in the top layer of soil. This agitation breaks up anaerobic conditions, increases oxygen exchange, improves soil structure, and reduces methane emissions, one of the most potent greenhouse gases in agriculture. Rather than trying to eliminate each problem with chemicals, the rice duck system allows biology to regulate itself. It is this reversal in logic that creates a fundamental difference and explains why the rice duck model is both praised as a sustainable solution and questioned within the framework of modern chemical-dependent agriculture. When ducks are released into rice paddies, the farmer's biggest concern emerges immediately: yield. No matter how balanced an ecosystem may be, it becomes meaningless if productivity declines. For many, introducing animals into actively cultivated rice fields sounds like an unacceptable risk. Yet, reality moves in the opposite direction. When managed correctly, ducks do not damage the rice. They are typically released about 2 to 3 weeks after transplanting. When the rice plants have become strong enough, rather than feeding on the crop itself, the ducks largely ignore the rice and focus on insects, aquatic organisms, and young weeds. As pest pressure decreases and soil structure improves, rice plants experience less stress. Their roots develop more steadily, nutrient uptake becomes more efficient, and growth grows increasingly uniform over time. At the same time, the paddy begins to change in visible ways. Beneficial insects return. Frogs, small fish, and dragonflies reappear. The water becomes clearer with less algae. The rice field no longer operates like a chemical-dependent production factory but gradually returns to the state of a living ecosystem. And once that ecosystem is restored, yield no longer has to be sustained by increasing chemical inputs. It begins to emerge from the stability of the system itself. The benefits of the rice duck system do not end at the edge of the paddy. As the season progresses, the ducks grow alongside the rice, drawing on a natural food supply of insects and aquatic organisms. As a result, they develop robustly without the heavy reliance on industrial feed or antibiotics common in intensive livestock systems. By the end of the growing season, the ducks are no longer merely ecological tools, but economic products. Farmers can sell duck meat or eggs, creating a direct source of income in addition to rice. For many smallholder households, this added revenue is enough to offset production costs and in some cases generate profit even when rice prices fluctuate. At the same time, the value of the rice itself changes. In many regions, rice produced under the rice duck system is marketed as ecological or low-chemical rice, often commanding prices 10 to 30% higher than conventional rice. Consumers are increasingly willing to pay a premium for products associated with environmental protection and human health. More importantly, this model helps farmers escape complete dependence on a single crop. Instead of placing all their risk on one rice harvest, they gain multiple parallel income streams. In an agricultural landscape growing ever more unstable, that very diversity becomes the factor that allows farmers to remain resilient. If the rice duck model in China carries the character of a grassroots revival driven by farmers' practice, then in Japan it was taken one step further: standardization. Beginning in the 1980s, Takao Furuno developed the Agamo method, transforming a traditional biological system into a tightly controlled farming process. The most distinctive feature of Agamo lies in its management discipline. Ducklings are released into the paddies at precisely calculated densities at exactly the moment when rice plants are strong enough and are removed before the rice enters the flowering stage. There is no room for randomness. Every step is designed to minimize risk to yields. As a result, igonal rice fields require virtually no pesticides or synthetic fertilizers. Yet yields remain comparable, often more stable than those of conventional chemical-based farming. More importantly, Agamo rice has been strongly embraced by the Japanese market, typically selling at a premium of 20 to 30% thanks to its reputation for quality and environmental responsibility. Compared with the rice duck model in China, Agamo makes one point clear. Biological farming does not rely on nature alone. It also demands discipline and scientific design. It is precisely this combination that has allowed an ancient method to survive and thrive within one of the world's most demanding agricultural systems. Despite its promise, the rice duck system is not a miracle solution that can be applied everywhere. In reality, it is a system that demands strict discipline and precise management. If ducks are released at the wrong time, when rice plants are still too young, an entire field can be trampled within hours. If they are removed too late, the ducks may damage the rice panicles during the most sensitive stage of the growing season. Ducks also bring their own set of risks. They must be protected from predators such as foxes, snakes, and birds of prey. This requires fencing, human supervision, or additional protective measures. Investments that not every farming household is willing or able to make. Water management presents another challenge. Unstable water levels can reduce the ecological effectiveness of the system or even cause it to backfire. More importantly, the economic performance of the rice duck model depends heavily on market conditions. Not everywhere are consumers willing to pay a premium for ecological rice or low-chemical products. Without suitable market access, the economic advantages of the system diminish significantly. For these reasons, rice duck farming is not a comprehensive replacement for industrial agriculture. Rather, it is an option that must be carefully evaluated, one that works best when matched with local conditions, management skills, and access to supportive markets. As the rice duck system began to show clear results, some farmers raised a follow-up question. If ducks can help rebuild the surface layer of the rice paddy ecosystem, then what is happening beneath the water? And could that ecological layer be used more effectively? Fish were introduced into rice paddies to take on roles that neither chemicals nor ducks could fully address, controlling larvae, plankton, and excess organic matter in the water layer. In this system, each component operates in a different layer. Fish live and feed below the water's surface, consuming mosquito larvae, insect eggs, and organic debris. Ducks operate at the surface, controlling pests and weeds while stirring the water. Rice occupies the growth layer above, benefiting from the activity of both. The three layers do not compete. They complement one another. Compared with traditional rice fish farming, the addition of ducks makes the system more closed and self-regulating. Fish handle what happens below the water. Ducks manage what occurs at the surface, and rice becomes the central recipient of nutrients. As a result, the need for fertilizers and pesticides continues to decline while the ecosystem remains more stable across multiple seasons. In parts of China, Vietnam, and Bangladesh, this model has proven especially effective under prolonged flooding conditions. When rice faces risks from floods, fish and ducks can still thrive, acting as an economic safety net for farmers. Instead of relying on a single product, they harvest rice, fish, and ducks from the same field. However, this system also demands a higher level of management. Fish density, the timing of duck release, and water level control must all be carefully calculated. Not every location is suitable, but in places where conditions align, the rice fish duct model demonstrates an important principle. When ecosystems are properly designed, agriculture does not have to choose between productivity and sustainability. The rice duck model is not a universal solution for every landscape or farming system, but it reveals a core insight. When agriculture is designed to work with nature, efficiency and sustainability no longer have to be opposing goals. China did not invent a new technology. Instead, it returned to a system that once existed, one that had been overlooked, and re-examined it through the lens of modern science. So, where does the future of agriculture truly lie? In inventing ever more technology, or in learning how to use more intelligently what nature has already provided?